Okay, so this is a talk about Morley's categoricity theorem, which is a theorem in model theory. It's a very recent work. I gave already this talk or a kind of an extended version in our own seminar at Masaryk University. And so this is of course the meta theory here is going to be classical. I apologize to the several constructivists that are in the audience, but I have to say, Eric always gave me a lot of freedom to work on whatever I liked, and I really much appreciate that, and I'm very grateful for that actually. So of course, the logic is going to be intuitionistic, infinite or intuitionistic logic, but the meta theory is classical, as we are dealing with classical theorems from model theory. Okay, so let's review a little bit of these categoricity theorems. So we have Morley's categoricity theorem, which says that a countable first order theory categorical in some uncountable cardinal is categorical in all uncountable cardinals. So it means if it has just one model up to isomorphism of a certain cardinality, then the same holds for every uncountable cardinality. So for example, the theory of algebraically closed fields has in every uncountable cardinality just one model up to isomorphism. And Morley says that this is the general behavior of categoricity to expect for countable first order theories. Then there's of course Scheler's categoricity conjecture, who did generalize Morley's theorem to, so there are several versions, but one version is for sentences in L omega 1 omega. And there, a countable theory T in L omega 1 omega, the logic with countable many conjunctions and disjunctions, but only finite quantification, is categorical in some kappa bigger or equal than Beth omega 1. So this is a certain cardinal. Then is categorical in all kappas bigger than this threshold cardinality. So there is an eventual categoricity there, behavior that you can see, and this still remains a conjecture, but versions with where you replace this threshold cardinal bar by an eventual big enough cardinal have been proven already, and there you can see that it's a generalization of Morley's categoricity theorem to these kind of logics. And of course, the eventual version is also stated for theories in L kappa omega. So you allow here the conjunctions and disjunctions to range over ordinals less than kappa, but you still keep the finite quantifications here. So this is still finite quantifier languages. The most general version of the conjecture is stated for an abstract elementary class, an AEC. In that case, well, we don't have really finite quantifier languages anymore. In fact, every AEC has been recently proven to be axiomatizable in some L kappa kappa for some kappa, and but the AEC shares a lot of features with finite quantifier theories. So and then the question is, of course, what happens in the more general case with this categoricity behavior in case of infinite quantifier theories? What about more general theories in L kappa plus kappa, for example? So, and I should mention here that these kind of logics are actually useful because there are a lot of concepts that cannot be axiomatized in finite quantifier languages, even if you use infinitary conjunctions and disjunctions, but they actually need finite quantifications, infinite quantifications, so to quantify over an infinite amount of variables simultaneously to be able to be defined. For example, Hilbert spaces or separable topological spaces, the notion of well-order, well-foundedness, cofinality, the notion of uncountable sets. All those are notions that cannot be axiomatized in a finite quantifier language, and they need the infinite quantifier theories. So what about the categoricity behavior there of these theories? And there is a result from Lieberman, Rosiski, and Vassey that the category of Hilbert spaces and isometries is one example of such a theory. It's axiomatizable in L omega 1, omega 1, and the categoricity spectrum alternates. So in fact, assuming GCH to simplify things, this theory is categorical in every lambda which is not of cofinality omega, and it's not a successor of a cardinal of cofinality omega either. So this is an example where we lose the eventual categoricity behavior. And so the question here is, what happens in general in this case? Can we recover some form of eventual categoricity for these theories, or can we describe more or less precisely the categoricity spectrum of the theory? One observation that they made is that this theory is actually categorical in every lambda if you modify the notion of size to that of an internal size, which is defined as follows. So first of all, this theory, the category of models of such a theory is an accessible category. I don't want to get into those details, but being an accessible category, you can define, there is a notion of internal size, which is this, the internal size of an object I in that accessible category. So a model, you think of it as a model of the theory, is kappa if the least regular cardinal lambda such that the object is lambda presentable is kappa plus. And in case that thing is a limit and not a successor cardinal, then it is itself. So this is internal size, and it happens that this category is categorical in every lambda with respect to internal size. This is because internal size, in the case of Hilbert spaces, coincides with the cardinality of an orthonormal basis for the space. And that is, in fact, if you fix a cardinality, then there's just one Hilbert space with a basis of that cardinality. So the intention here is so this is in L omega 1, omega 1, but I want to study theories in the more general logic L kappa plus kappa. So inspired by this result of these people, I would like to generalize the notion of Hilbert space to deal with that of a mu Hilbert space, which would be something axiomatizable in L mu mu. And so to do that, I need to define what is a mu field. R is just a field of hyperreals that contains all ordinals up to mu. So I'll briefly describe the construction here. So you first take the initial segment of the ordinals up to mu. And then, of course, it has some operations, but the natural operations, which are less known, also called Hessenberg operations, are defined as follows. So, for example, if you want to define the natural sum of A and B, you take the partial order of A, the partial order of B, you take the disjoint union of those, you get a partial order, you use the axiom of choice to extend it to a linear order, and then from all those possible linear orders that you get, they will be actually well orders, and you can compute the order type of it as an ordinal. The maximum of those, the supremum, is going to be the ordinal sum, natural sum of this. And for the product, is the same. It's just that instead of disjoint union, you take a direct product here. So this sum happens to be actually commutative, associative, and in fact, the sum distributes over the product distributes over the sum. So you have the distributivity property there. And these operations can actually be carried on while we build the hyperreals in the next stages. So we build the corresponding ring of mu integers once we have this mu naturals. Then we take the field of fractions, and finally we take the mu completion of that field, considering all mu Cauchy mu sequences. So a mu sequence is just, of course, a function from mu to the set of fractions, and is mu Cauchy if it's the same definition of a Cauchy sequence, except that we allow the n that we take big enough to be beyond omega. So it could be for any ordinal less than mu n. After that n, the difference between any two members of the Cauchy sequence is less than any epsilon that is already in the field of fractions. So it could be not necessarily a real number, but actually it could be an infinitesimal. So we got infinitesimals once we inverted the infinite ordinals here in this step when taking the field of fractions. Okay, and then a mu Hilbert space is just a Hilbert space, but instead of taking the field R of reals, you take the mu field of hyperreals. And so here, the observation is that if you have an orthonormal base of size lambda, then each element of the mu Hilbert space has at most mu non-zero coordinates. In the case of the usual Hilbert space, we have at most countable non-zero coordinates, but here, because we're working with, we have infinitesimals, we have more space to put non-zero coordinates. So this has the consequence that the cardinality of any mu Hilbert space is of the form lambda to the mu. And this is already enough to know what the categoricity spectrum is going to be like. Because to simplify, if we assume the generalized continuum hypothesis, then lambda to the mu can be computed according to the value of the cofinality of lambda, and always supposing that 2 to the mu is lambda. But we suppose mu fixed here, and lambda is going to be big enough. So this means that eventually, for lambda big enough, there is exactly one mu Hilbert space for every cardinality lambda, which is a regular cardinal and not a successor of a cardinal of cofinality less than mu. And however, there are going to be two mu Hilbert spaces, which will correspond to Hilbert spaces of sizes lambda and lambda plus, if in the case it is the successor of a cardinal of cofinality less or equal than mu. So here again, the categoricity spectrum alternates, but what I want to, what we will see essentially from the version of Morley's theorem that will hold is that these will be the only exceptions in this setting. Assuming the generalized continuum hypothesis, these, the being of a cardinal, not a successor of cardinal of cofinality less or equal than mu, those will be the only regular cardinals for which the theory is not going to be categorical, assuming categoricity in one regular cardinal, not of this form. So that would be like the Morley version for these infinitary theories. And so to prove that, we have to recall a little bit. Okay, and then the observation, of course, is that if you compute the internal size, again, it's categorical in every lambda. So you recover the eventual categoricity literally if you work with internal size. So we have to come back to the lambda classifying toposes to see how's the proof idea behind all this. So let me remind you, let's work first in the setting in which we use cardinality of the underlying model. I call T kappa plus the theory consisting of T, the theory axiomatizing these models, plus the sequent expressing that there are at least kappa plus distinct elements. So that will be it can be a sequent in in an infinitary logic. And one thing that I remember I spoke about this in one seminar at Stockholm once, introducing this notion of kappa plus classifying toposes of this theory. So let me just recall what it was. So it's a kappa plus topos. A kappa plus topos is what I call a topos which has a certain transfinite transitivity property, which says that a transfinite composite of jointly epic families of arrows in the topos is itself jointly epic. So that's a kappa plus topos if the transfinite composition goes up to kappa plus, strictly less than that. And the kappa plus classifying topos of such a theory is a kappa topos with the universal property that for any other kappa topos, a kappa plus topos E, models of the theory in E correspond to geometric morphisms whose inverse image preserve all kappa plus small limits. So this is the generalization of the usual notion of classifying topos for geometric theories. Here is just that you have an infinitary geometric theories in the sense that you can have also infinite disjunctions here, and infinite variables that are existentially quantified. And the main result of that one uses for this Morley extension theorem is what happens when we compute the lambda classifying topos of a kappa theory for lambda bigger than kappa. And so if T kappa axiomatizes the category of models of size at least kappa, which I denote by K bigger or equal than kappa, the lambda classifying topos of T kappa will be equivalent precisely to the pre-shift topos on the lambda presentable models of T kappa. And in fact, the canonical embedding of the syntactic category is given by the evaluation functor. So we take a formula here and we send it to the functor which in a model evaluates the extension of the formula within the model. So that's what happens. And using this, we can take a look at, so one big important step in the proof is to say what happens with the saturated model. So I'll introduce this notion here. A model M is mu plus saturated if for every morphism from n to n prime between models of size mu, any map from M to M can be extended to a map from n prime to M. And using the previous theorem that computes the lambda classifying topos of kappa theories, then I was able to compute the classifying topos of the kappa plus saturated models. So first of all, it happens that the Such a notion is axiomatizable in this logic, and the kappa plus classifying topos of the theory of kappa plus saturated models will be precisely the topos of sheaves on the subcategory, the full subcategory of models k kappa of internal size kappa with the dense topology. Since we are assuming amalgamation in this category of models in general, which would correspond to the right order condition in the opposite category, the dense topology will coincide with the atomic topology. So this will be, in fact, sheaves. This will be precisely the double negation subtopos of the kappa plus classifying topos of T kappa plus. And so this is what allows to consider, to study better the saturated models of size kappa plus. Because the only thing to do is to prove categoricity is just to know that if we have that any model of size kappa plus must be kappa plus saturated, because there is a result that we will see that says that any two kappa plus saturated models of size kappa plus must be isomorphic. And so where do large cardinals come in this result? To get the amalgamation property, without which we cannot make that reduction from the dense topology to the atomic topology. So the main results here are that if kappa is a strongly compact cardinal and you have an accessible category K or a category of models of some L kappa kappa theory, then categoricity in a cardinal above the strongly compact cardinal gives you automatically the amalgamation property after the strongly compact cardinal. So this is a result that was known for the case of AECs, but here this happens to hold in general for any L kappa kappa theory. And so that's one way to get amalgamation. And then there's another result, which is the one I mentioned, that you get two lambda plus saturated models of size lambda plus to be isomorphic here, just under the assumptions that you are above a strongly compact cardinal. So the fact that they are isomorphic was proven by Rosiski using a Moore hypothesis, using a joint embedding and directed colimits in particular. But here, the fact that we're using this large cardinal will give us amalgamation, will give us no maximal models, which is that every model can be embedded strictly embedded in a bigger model. And then there's no need for joint embedding. And we can get actually this behavior of the saturated models without using directed colimits, all thanks to the large cardinal hypothesis. So the main result, if you phrase it in the language of category theory, it will say that if you have an accessible category with directed colimits, you have an eventual categoricity behavior with respect to internal size, as long as you assume the generalized continuum hypothesis and the proper class of strongly compact cardinals. Alternatively, you have the version of Morley's theorem with, you have to put those exceptions that we talk about, the not being of cofinality less or equal than mu, and not being a successor of a cardinal of cofinality less or equal than mu, and those will be the only exceptions in this setting for categoricity. And to mention the proof sketch of this result, I will just show these diagrams here. So this was the kappa plus classifying topos of T kappa, thanks to one of the theorems we had before. And then we can take a quotient theory, which just says that there are kappa plus distinct elements. So that's a quotient theory corresponding to a subtopos of this. I'm just putting here the inverse images of the geometric morphisms. And then we have, this happens to be a dense subtopos. So we have the double negation subtopos, which was the classifying topos of the kappa plus saturated models here. And if we take a model M of a size bigger than kappa plus, where we know lambda, let's say, where we know that the theory is categorical, then the fact that it's categorical implies in particular that is kappa plus saturated. And so by the universal property of this shift topos, this model will factor through here. So the idea is to prove that any sequent, any kappa plus geometric sequent valid in this subtopos is valid here as well, because that will prove that all models of cardinality kappa plus are kappa plus saturated and so isomorphic. And to prove that, we consider the evaluation factor now from the classifying topos of all models of size kappa plus to this pre-shift topos. Here, lambda is the categoricity cardinal. And there happens to be a version of Joyal completeness theorem for the infinitary setting after a strongly compact, in which we have that this evaluation factor preserves certain universal quantifications, certain right adjoint to pullback factors that live in these topos. So knowing that there is a categoricity cardinal here and that every sequent valid here should be valid in M, thanks to this factorization, we know that is going to be forced by the model of size lambda in this pre-shift topos, and therefore the pre-shift topos will force the double negation as a consequence, which means that the double negation of the sequence should be valid here, since this preserves universal quantification. And this happens to be a two-valued topos because we also assume categoricity in kappa, which makes this two-valued and hence this two-valued. And so the sequence is valid there automatically. Then I want briefly to mention, I don't have much time, but just one extra result regarding the relation between eventual categoricity and amalgamation. If you assume these cardinality conditions, sorry, I haven't defined what S is, but it doesn't matter for the moment. It just means that it's not one of those cardinals that we put in the exceptions in the Morley theorem. Then the category of models of size kappa has the amalgamation property if and only if the pre-shift on that category is a De Morgan topos. So in particular, this means that any such sequent for kappa plus coherent or geometric phi is valid in the pre-shift topos. And a consequence of that is that if you have categoricity both in kappa and kappa plus, then K kappa will satisfy the amalgamation property. So this actually shows that amalgamation is really needed for if we want to prove categoricity theorems for these kind of theories. So okay, so the proof is very simple. We just compute the kappa plus classifying topos of the kappa, and we prove that it has to satisfy all sequence of this form, because if not, you take the quotient theory with those sequence and you show that it has to be a topos here which is strictly containing these two, but it cannot be this one, and there is nothing intermediate here, so it has to be the whole pre-shift topos. And the very last work on in some results you can actually remove the generalized continuum hypothesis through forcing arguments. So how do you do it? The main reason why we needed the generalized continuum hypothesis was to be able to say that kappa to the less than kappa equals kappa, which is needed for the completeness theorem for these kappa plus geometric logics. However, what we can do is try to introduce a forcing that collapses k to the less than kappa to kappa, sorry, in the sense that we introduce a new bijection between these two in the universe of sets without affecting the main properties of the models of cardinality less than kappa. What do I say? So, for example, the previous theorem on amalgamation used this condition. So we have a certain universe of sets, B, and if in B, this equality does not hold, so if this k kappa plus to the kappa is strictly bigger than kappa plus, we consider a forcing extension, VG, in which we add new sets. In particular, we add a bijection between these two. So collapsing k kappa plus to the kappa 2 kappa plus. In these new sets, well, what happens is that this forcing has a property which implies that any function in the new universe of sets, which goes from kappa to V, so has codomain V, actually belongs to B, to the previous unit, the original universe of sets. So using that, we can see that we don't add any new subsets of sets of ordinals of cardinality kappa. And since models of size less than kappa plus and their embeddings can be coded by ordinals less than kappa plus, less than kappa, in fact, then we can assume that the category of models k kappa does not change. So if k kappa satisfies amalgamation in the new universe of sets, it is because it already satisfied it in the previous one. And so you prove by using finally the completeness theorem for finitary logic that amalgamation is provable already in your original universe without the the arithmetic hypothesis here for cardinals. But I should stop here. Thank you.
Thank you, Christian. Let's thank Christian with a silent applause. All right. Any questions, comments?
I had one which I'd been thinking was maybe too dull for the questions that I'd ask offline, but if no one else is asking. So I very much liked, I was very intrigued by some of your results that were connecting the infinitary logic properties to the properties of the classifying toposes. Things like the one about the amalgamation property corresponding to being a De Morgan topos. Mm-hmm. And then both of those, they have the feeling of the kind of properties that are sometimes controlled by some more elementary or more combinatorial property of the cardinal. And I was wondering if some of these results that sort of the cardinal has some property related to the logic, if it has some property related to the classifying topos, can it also connect them to any sort of simpler, more elementary combinatorial properties of the cardinals or something? Or
for the case of amalgamation, I'm not aware of any result which just talks about the combinatorial property of the cardinal, because so the result for amalgamation being a De Morgan topos, and for the omega case, so for the case of countable models of a first order theory, is already known. So the contribution here is that the same holds for any other cardinal satisfying this cardinal arithmetic hypothesis kappa to the less than kappa equals kappa, because it's a consequence of the completeness theorem for these infinitary logics. But I'm not aware of any strictly combinatorial condition that could result in the amalgamation property there.
I can also ask a question. Hi, Chris. so I, as far as I know, one of the tools that Sheila used to prove the Morley's conjecture and his classification results is called the elimination of imaginaries of a theory of a structure.
Yes.
And actually, there is a very close connection between the elimination of imaginaries and quotient completions.
Yes.
That I and actually I will speak about these quotient completions. I mean, it's also part of the work with Rosolini and Pasquali. But I started like looking into this connection because of a suggestion of Eric. So I was wondering if you're using this elimination of imaginaries, if it plays any role in your...
The answer is yes. So there is a notion of kappa plus pretopos completion for these syntactic categories of theories in L kappa plus kappa. And in fact, I had used, you have a note that you have written for Eric on this relation between Sheila's elimination of imaginaries and the pretopos completion, which I have used to generalize the same setting in this infinitary case. So thank you for that.
Oh, that's actually very interesting, because in the paper that I have with Pino and Fabio, we generalize that further. So we show that it's not just a pretopos completion, but it's an instance of something more general.
Right. Yes. So yeah, you can consider the kappa plus pretopos completions, which will be a pretopos with a kappa plus small coproducts, and which satisfy this transfinite transitivity condition up to kappa plus.
Okay. And okay, then one more question. Sorry, this elimination of imaginaries. I was wondering, is that used also to prove the completeness results that you were mentioning before?
The completeness results?
Yes, for the.
No, you don't need it, because you can just work with the syntactic category. You don't need it to. Oh, okay. You don't need to upgrade to the kappa plus pretopos completion. But if you do, you will see that they have equivalent categories of models.
Right. Yes. Okay. Thank you.
Okay. Thank you, Jacopo. All right. I think it's time to thank Christian again with another silent applause. And then we are